So the first thing that we could do is just to verify whether device initialization is successful, right? So we haven't changed the rate or the baud rate for any watt, right? So by default, whatever it is set in a block diagram, the same rate it will be working, that is 115200, right? So we'll just go ahead and first try to program an FPGA, right? This is the first step that we follow once we complete development of an application. Now what we're going to do is we will just be connecting an SDK terminal. So I have my FPGA at COM4 and we'll be setting up the default baud rate, right? That is 11520. Then we'll proceed execution of a code. Now we are already calling UART init. So this will initialize our driver and we are expecting to see UART initialization successful message, right? Now you could see we are receiving UART initialization successful, right? So this basically suggests that our initialization process is completed successfully, right? Now you could utilize the functions which we used in the past, such as ZYNQ to send the data to a console, okay, and that will also work fine. So we'll just go ahead and try to add ZYNQ. Okay, here let's just add hello world, right? Now if you just save a code and try to again relaunch a simulation, now these functions will work similar to our previous case because we successfully able to initialize our UART, right? Now you could see we able to see hello world, right? Now what we could do is we could just try to utilize the APIs that we have in our header file just to explore, okay, the different things that we could do with UART-PS, right? So let us just go ahead and try to just go through with the different APIs that we have, right? So we have something called a set baud rate that could be used to set a user specific baud rate, right? So again, going back to a block design and changing a baud rate will be a difficult process, right? So if you just remember, when we reconfigure IP, okay, and when we go to a PSPL configuration, you have a general tab. So there you could see we have a baud rate option for our UART1. Now here we could go and change. This is one of a method that we have, but once we reconfigure it, we need to again perform all the process, right? And then that will be an updated hardware specification that we will be invoking in an SDK, right? So that is the one of the process that we have with us. The next one could be, now we could utilize the APIs that we have, right? So software allows us to dynamically vary a baud rate, and that is what we will be demonstrating first. So let us just copy this code, okay, go ahead. Now just before and hello world, okay, we'll just be utilizing set baud rate, right? So these have two arguments. First one is an instance structure and second one is a baud rate, okay, which is the value of baud rate that we want to set, right? So for us, an UART instance structure is UART, right? And the baud rate that we're gonna see is 9600. This is the baud rate that we wanna set. Okay, let us just save our code and try to again relaunch a simulation. Now SDK terminal is configured to work at 115200. Okay, so you do able to see a data which could not be recognized, right? Because SDK is operating at a different rate and our UART is configured to operate at different rate, right? So we'll just be clearing up the console. We'll be disconnecting our SDK terminal. Go ahead to connect an SDK terminal and we'll just be changing the baud rate to whatever baud rate that you have specified, right? So once you do this modification and try to execute the code, okay, so now you could see hello world is printing correctly, right? So this is allowing us to, this step allowing us to dynamically vary a baud rate, right? So this is the advantage that we get when we work around with the APIs for the specific peripheral, right? Now what we're going to do is, instead of utilizing a ZYNQ, let us just explore the APIs that are available for sending and receiving a data, because these are the two most frequent things that you'll be doing with an UART, right? So instead of utilizing the abstract functions such as ZYNQ, we could always work around with these functions that are available, right? So we have XUART-PS send, okay, which could be used to send the data specified in a buffer to the console, right? Now this operate again in a two mode, so it could either be a pooled mode or an interrupt driven mode. Since we have not discussed anything related to an interrupt, we'll not be understanding it right now. Okay, instead we'll be utilizing a pull mode. So what we'll be doing in the pull mode is we'll be specifying a buffer. Okay, then we'll start transmission, and then we gonna continuously check whether sending is complete or not, right? So whenever we need to wait for certain process to complete, that is what we refer to as a pull mode, right? And in an interrupt driven process, so as soon as our process of sending is completed, we will automatically getting a notification from an interrupt that our transmission is complete, right? So this will be the differences that we have. We'll be predominantly focusing on a pull mode right now because we haven't covered anything related to interrupt, right? So let us just first tackle how we could send the data, right? And if you just click an F3 to explore what this returns, right? This again requires 3 arguments. So we have an instance structure, you have a buffer pointer, right? So this could be simply the name of our array of the data that we're gonna send, right? That could also serve as the pointer for our entire data, and then the number of bytes. So these are the 3 arguments that we have for our send, and then this basically returns U32, right? So and this returns the number of byte actually sent, right? So we will be specifying a bit. So this basically mean that the byte that we specify, the number of byte that we specify for our transmission may not be sent in a single go, right? So we need to, okay, so in a pull mode we need to continuously sending up the data. Okay, so the maximum capability that we get is we could send max as much data as TXV4 can buffer. Okay, so this is the maximum capability that we get. Whatever the size that we have for our TXV4, that is the maximum data we could send. Okay, and then any data greater than the TXV4 size, we need to repetitively send it, right? And then in a pull mode, we need to wait until the data transmission is complete, right? That we already discussed it. Now in interrupt mode, the interrupt handler will continue sending the data until the entire buffer has been sent, right? So this is something different as compared to pull mode, right? So here we need to take care of whether all the data is sent or not. In an interrupt mode, the interrupt handler will continue sending the data or will take care of our entire data, right? So remember this fact. So first argument is the UART instance structure. The second one is the pointer to a buffer of a data, and third one is the number of bytes that we want to send. And this basically return the number of bytes which are sent, right? So let us just go ahead to our main application. Okay, and here we will be declaring, let us assume, one array of U8, right? Now you could clearly see that we send byte by byte, right? And that could be observed like this. So here we are expecting a pointer of U8 type, right? So this basically means we are sending the data byte by byte. So let us just declare U8. Okay, exactly the same type that our function is expecting from us, and we'll just be naming this as data. So we will not be specifying the size because we're gonna specify static data over here. Okay, so let us just call an hello world again. Okay, and then we'll not be utilizing ZIL printf now, right? So this is an array, okay, of U8 where we store the data that we wanna send, right? Now we'll be counting the number of bytes that we require, right? So for each character we require a single byte. So 1 2 3 4 5 space consists of 1 byte, right? So 6 7 8 9 10 and 11, right? So we have total 11 byte that we are planning to send, right? So we already set up a baud rate. Now we'll just be calling the send function that we have, right? The first thing that we specify is an instance, which is UART, right? The second thing is the pointer to our data buffer, right? So we could just be accessing it by specifying the name of our array, right? That is data, and then the number of bytes that we are targeting, that is 11, right? So once you do this, now since we are working in a pull mode, so we'll not be getting automatically any indication whether data is sent or not, right? So this function do returns us the number of bytes which are sent. So we could just be comparing whether all the data bytes, that is 11 bytes, are sent or not. So as soon as our count reaches to 11, okay, we will be coming out of loop. Else we could just be waiting there. Or other option that we have is, so what we could write over here is, if let us just declare one int, okay, and that will basically be storing byte send, right, and this will be attaching over here, right? So byte send. So if byte send is not equals to 11, we'll just be sending the data, okay. Now that basically means as soon as byte send equals to 11, as soon as we send all the data, we will just be coming out of this loop, right? Now byte send will be initializing to a 0, okay. So let's just try to go ahead and see whether this is working as expected, right? So we'll just be clearing up the console, and now we'll again be relaunching our application. So if you analyze an SDK terminal with this logic also, we could able to send an hello world, right? So what is happening over here is we are waiting till the byte count reaches to 11, right? This is one of the method that we have. Else the other method could be, now this is again a pulled method because we are waiting till byte send reaches to 11, right? So we are not getting any direct notification from the peripheral, which we could get with an interrupt, right? Now we could utilize the same logic, but here instead of utilizing this one, we could just go ahead and try to look for an API which could be helpful in this specific scenario. So we might be having an APIs that could be used to wait until UART completes sending a data, right? So here you could clearly see we have UART-PS is sending. So if you explore this function, now this function determines if the specified UART is sending a data, right? So if UART is sending a data, it will return true, else it will return the false, right? Now this function could be utilized to wait till we send the mentioned byte, right? So while we'll just be specifying this function, and this just require the instance, right? So the instance structure is UART. Now what will happen is if we add code like this, so we send the data, okay, and this will be true, okay, until we are sending a data. So until we send an 11 bytes of data that we specified over here, this will be continuously returning us true, and when while is true, it will be waiting over here, right? So as soon as we complete sending all the data, what will happen is this will return false, right? So as soon as this return false, so while 0, this basically means false, so we'll be coming down right over here, and then we'll just returning a 0, right? This is an entire code that we're gonna work. So let it just clear our previous output and try to perform a simulation again. So this is the second way that we have. Again, we are waiting, but here we are utilizing the API that we have with UART-PS, right? Now again, you could see we are getting the same result, right? So here we understood how we could vary a baud rate on a go, and the second thing is how we could send the data. Now what we gonna target next is this data that we are sending, we'll try to receive back a data, and then we'll just be comparing whether data that we have transmitted is matching to the data that we are receiving, right? So that way we will be understanding how we could receive the data from a UART.